Hi, I am Professor N.K. Pandey from Department of Physics, University of Lucknow. And this is again here that we are meeting for a topic in quantum mechanics. And although I have given already a lecture on this, the Broglie waves, and have uploaded this one on the YouTube, but comprehensive view of the Broglie waves or the matter waves related with or associated with a moving particle needs to be understood. A comprehensive view is needed to be understood, and therefore this is a new lecture I am having, in which I have started with the Broglie waves and I have gone up to the Schrödinger wave, and in between I have shown the continuity between the what we call the Newtonian or the classical mechanics and the quantum mechanics. And it will be seen that the progression from the classical mechanics to the quantum mechanics, although it seems to be a quantum jump, but certainly it is not. Rather, it's a continuity of the classical mechanics that is there in the quantum mechanics. So let us start with this lecture. And we will start with the three experiments in the beginning of the quantum mechanics. One is the photoelectric effect, the second is the Compton effect, and the third is the Davison and Germer experiment. Now, in the photoelectric effect, what we do? We have electromagnetic wave in the ultraviolet region that is irradiated on a metallic surface. The electrons are ejected, and these electrons reach this positive cathode, and they constitute a current in the external circuit. Now, if we try to explain photoelectric effect on the basis of electromagnetic wave theory, the classical electromagnetic wave theory, then if we irradiate the surface with ultraviolet rays today, then according to electromagnetic wave theory, we should be getting the electrons at least after the elapse of 1 year. Whereas we know that the ejection of electrons are instantaneous once the ultraviolet rays fall on the metallic surface. More so, other such results of the photoelectric effect is also not explained on the basis of electromagnetic theory. And therefore, the quantum theory had to come up, and Einstein gave this relation h nu, that is the energy of the incident radiation, h nu naught, that is the work function of the metal, and T maximum is the maximum kinetic energy taken away by the electron. Now here we have to understand that this was explained on the basis, initially we can say Max Planck, while studying the radiation from a hot body, had given the view that the electromagnetic radiation came out of the hot bodies in the form of small bundles or packets of energy, and he called them quanta. He said that although these radiations were coming in the form of quanta, they propagated like electromagnetic waves continuously. However, later Einstein did accept that electromagnetic waves came out of the surface of the hot bodies in the form of quanta, but he opined that they propagated as well as quanta and not continuous as electromagnetic waves. So the final view was that the electromagnetic waves that we call, these are ejected as photons, and they travel also as small packets or bundles of energy called quanta. So this was the result of the photoelectric effect, and photoelectric effect could be explained only on the basis of quantum theory. Now let us go for the next one, that is the Compton effect. Here the electromagnetic radiation in the form of X, in the range of X rays, are scattered from a quasi-free electron, and in the scattered radiation we have the photons which have both the wavelengths, the initial wavelength of the photon as well as the larger wavelength of the photon. Now the presence of original wavelength in the scattered radiation could be explained on the basis of electromagnetic wave theory, but certainly the presence of higher wavelength could not be explained on the basis of electromagnetic theory. And there the quantum theory had to be brought up, and with the help of quantum theory, this Compton effect could be explained. And we got over there the change in wavelength is equal to h by m naught c1 minus cos phi. Here lambda dash is the wavelength of the scattered photon and lambda is the wavelength of the incident photon. H by m naught c we call the Compton wavelength. Phi is the angle of scattering. Now let us go for the third experiment, that is the Davison and Germer experiment. Here the accelerated electrons are made to fall on a nickel target, and in the nickel target, on being hit, when the nickel target was heated, then their atomic planes were arranged in regular fashion. So when these electrons are made to be incident on the nickel target, classically we should be expecting a uniform distribution of electrons in the scattered beam, whereas there were maxima and minima present in the scattered beam as detected by the electron detector. Now, this maxima and minima are the properties exhibited only by waves and not by particles. So here we had a different story than what we had in the photoelectric effect and the Compton effect. In the photoelectric effect and Compton effect, we had waves behaving like particle, and here electrons were behaving like waves. And in the Davison and Germer experiment, the Bragg reflection formula was used to explain the presence of maxima and minima in the scattered electron beam. Now, so we have this as conclusion out of these experiments: photoelectric effect and Compton effect. They conclude, from there we can conclude that waves could behave like particles and could make collision with other particles like billiard ball collision. Now, Davison and Germer experiment, it gave moving particles like electrons could behave like waves. So we have waves behaving like particles and particles behaving like waves, and therefore if we take the energy of a photon, that is E is equal to h nu or E is equal to hc by lambda, and the energy is also given by the formula E is equal to square root of m naught square c power 4 plus p square c square. Here m naught is the rest mass energy and p is the momentum carried by the particle. Then since photon does not have any rest mass, so m naught is equal to 0 and therefore E is equal to pc. This implies that hc by lambda in the first line becomes equal to pc. This implies lambda is equal to h by p. So we can understand over here that this is the relation that joins the wave and particle properties. Lambda is the property exhibited by waves and p, that is the momentum, is the property exhibited by particles. So particles are behaving like waves and waves are behaving like particles. So we are in the realm of now wave particle duality, and we have a conclusion that moving particles can be associated with a wave. We call that wave the Broglie wave or the matter wave. Now the question next one arises: if there is a wave, we call the Broglie wave, or we call that the matter wave. If there is a wave associated with a moving body, then what kind of this wave function psi is? Of course, we will be understanding the properties of psi little bit later, but for the beginning, this wave function psi associated with a moving particle is a complex function, and because it is a complex function, it can be written as a plus ib, where I stands for imaginary and psi star is equal to a minus ib. So mind it, the modulus square of this psi is a real quantity. Now this mod psi square, we will see later that this is defined as a probability density and is given by the product, that is the complex conjugate of psi, that is psi star and psi, the product of psi star and psi. Next question that arises, that if this wave is associated with the moving particle, then what is the speed of the Broglie wave? Now our common sense will tell us that since the Broglie wave is associated with a moving body, this wave should travel at the same speed as that of the body. Now, we may quote the usual formula. Lambda is equal to h by p, that is mv, by the previous formula. E is equal to h nu, that is mc square. So nu is equal to mc square by h from the two above formulae. And therefore, the speed of this wave is w is equal to nu lambda m, that is Finally, it comes out to be c square by v. Now, the question is, the Broglie wave here has a speed greater than the speed of light in vacuum or the moving body? Greater than the speed of light in vacuum. Now, this is unreasonable. Is it okay? Now, we need to look into a different perspective. But initially, let us understand two things. There are two speeds here. One is the wave speed or the phase speed, and the other is the group speed we call. Now, phase speed or wave speed is given by omega by k, and group speed is given by d omega by dk. Nothing physical moves with phase or wave speed, and energy or physical quantity will move with group speed. For example, to understand it in a very clear way, to make some good picture about it, you can think that you are just thinking that you have reached Calcutta in no time. You are present over here, your mind has gone over there. So it is something correlated to your phase speed, that your mind is there, but physically you will go along with the speed of your body. So this is the difference slightly, somewhat between the phase speed or wave speed and the group speed. We will deal it slightly later also. Now, next question is, if there is a wave associated with a moving particle, then how to represent this wave? Now, does it look like a sinusoidal wave or a triangular wave, or what kind of a wave this we can associate with? Then, now, can the following equation of a plane progressive wave represent the Broglie wave associated with a moving particle? And what is that? Very simple, plane progressive wave. Y is the displacement of the particle. Y is equal to a sine omega t minus kx. A is the amplitude, omega is the angular frequency, k is the propagation constant. Can a plane progressive wave, whose mathematical expression is written like this, represent the Broglie wave associated with a moving body? And this is this wave. Now, if you see this figure of a sinusoidal wave whose mathematical expression is written above, then you can see this wave extends from minus infinity to plus infinity. Naturally, if there is a wave associated with a particle, then the stretch of the wave must be finite. Why? Because the particle is a localized entity. So any wave that we associate with a moving particle must be a finite, very close to the particle, and not extended to from minus infinity to plus infinity. So there is certainly a point that this kind of sinusoidal wave cannot represent the Broglie wave associated with a moving particle. Now, how can we represent this kind of a wave then? Then, mathematically, we can say that such plane progressive wave, like the one we have seen, y is equal to a sine omega t minus kx, these kinds of infinite series of waves, each one differing from each other in omega by d omega, in k by dk. On superposition of these kinds of infinite series of waves, we will be getting a single wave packet. And that wave packet represents the wave associated with a moving particle. That means, mind it, here we have, this is what I have written over here. Now let us see, if we have one wave, psi 1 is equal to a cos omega t minus kx, and this wave is represented like this. We have another wave, just like a plane progressive wave, psi 2 is equal to a cos omega plus d omega t minus k plus dk x. And this wave will be represented psi 2 by this one. Only slight difference in frequency, etc. are there. Now, the superposition of psi 1 and psi 2 is going to give 2a cos omega t minus kx cos d omega by 2 minus dk by 2. And this will be represented by this figure. Now, mind it, you can see from here that this cos omega t minus kx that is written over here, this one, this is having almost the same as the frequency of this and this, or the average of the two. And the amplitude of the resultant is twice a cos d omega by 2 minus dk by 2. So this figure, the envelope of this particular wave group, that has a frequency d omega by 2, and that has the propagation constant dk by 2. Now inside, this frequency is same as omega. So the frequency of this envelope is d omega by 2, and propagation constant dk by 2. Now mind it, so this kind of a wave group, this is the envelope of this one. This envelope will represent a wave associated with a moving particle, so that the particle is located somewhere in between from this end to this end. Now, if you see it, then this resembles Beats phenomenon in what? Beats phenomenon in sound waves, where you have two tuning forks of frequency 250 hertz and 252 hertz. Let us suppose you vibrate once, first one having a frequency 250 hertz, it will start with a humming sound. Similarly, if you pluck the other one, then again you have a humming sound, almost similar, having a slight difference in frequency. And the superposition of two is going to give you that this one we are representing here, it will give you that is, there will be maxima and minima in the sound that you listen. And if the frequency difference is 2 hertz, then you will have 2 maxima and 2 minima over here. So it has a resemblance in sound waves in the beats phenomenon. So you can also call these ones the quantum beats. So one difference you can understand, and that difference is that if you have only 2 such waves superimposing, then you will get large number of such wave groups. And so many wave groups cannot represent a wave associated with a moving particle. But if such waves are infinite in series and they superimpose, then the resultant will give you one such wave group, and this wave group will represent the wave associated with a moving particle. So now let us go back to the what we call the wave speed and the group speed. Now omega is equal to twice pi nu. Twice pi nu is equal to twice pi mc square by h. This m is equal to m naught by under root 1 minus v square by c square. This m at the end should be read as m naught. Similarly, k is equal to 2 pi by lambda, 2 pi m by v, and m is equal to m naught. Here it is m naught, correct. H under root 1 minus v square by c square. Then w is equal to omega by k is equal to c square. Mind it, w is equal to omega by k is the phase speed that I have explained. It can have a speed greater than the speed of light in vacuum. But if you differentiate the above to d omega dk, then you will get u is equal to v. That is the speed of the particle, and the wave group has the same speed. That means the wave group that we have seen just now, this one associated with a moving speed, will have the same speed as that of the particle. And the particle will be somewhere located somewhere from one end to the other. Now, as we have seen, because we are associating a wave with a moving particle, then naturally, particle which is a localized entity, we are making the localization of the particle uncertain, at least to the extent of the stretch of the wave. For example, if we have a broad wave packet associated with the moving particle like this, then you can see that here it is easier to understand, to estimate the wavelength of the wave, but the location of the particle becomes uncertain as to where it is located from here to here. But if we have a narrow wave packet like this, then the finding of the wavelength becomes tough, but the location, the determination of the location of the particle becomes easier to establish over here. So an uncertainty is introduced. I'm not going into the details of the uncertainty principle. I've already recorded a lecture on uncertainty principle, and it is uploaded on the YouTube. You can visit over there for this. Now, the moving wave packet or the Broglie wave. Now here you can see an animated picture of the Broglie wave. You can see the group is moving as such. So this is the moving wave packet or the Broglie wave associated with a moving particle, a typical one. Now this is the link I have given, courtesy to them. Now, what are the properties of the wave function? We have seen that it is a complex quantity. We have seen that it has the same speed as the speed of the wave. We have seen that a wave group represents a wave associated with a moving particle. The wave function psi is there. Psi is a complex function. So what are the properties of this wave function psi? So Number one, psi must be a solution of Schrödinger equation that we will come a little later. It must be a continuous function of x. The slope of the function in x must be continuous, that you know. Specifically, d psi dx must be continuous. And one more, very important point. The solution of the Schrödinger wave equation will give the wave function psi, and psi will contain all the information about the particle. All the information about the particle will be inherent in psi. And other one, psi should be normalizable. That is, naturally from minus infinity to plus infinity, the particle must be somewhere. And mod psi square is the probability density. So integration over this probability density from minus infinity to plus infinity should result in 1. The result will be 1. Now this minus infinity and plus infinity is simply a point that we have to understand is the extent of the wave or the wave group associated with the particle. From one end to the other, the particle must be located, and integration from one end to the other of the wave group will give you mod psi square dx is equal to 1 integration. Now, let us see mathematical expression of the wave associated with a free one. Now, there are two types of particle. One is a free particle. It has only kinetic energy. Another particle is there which is acted upon by a force. And if it is acted upon by a force, there is an interaction. And if there is interaction, there will be some interaction potential. So, a free particle has only kinetic energy, and a particle acted upon by a force will have some potential or potential energy. So, we are talking about a free particle. Now, this is the expression of a plane progressive wave also, or we can say over here, this is an exponential form that we have written the same sine or cosine function. So, psi is equal to a e to the power of minus I omega t minus x by v. On slight modification, this will give you psi is equal to a e to the power of minus twice pi I nu t minus x by lambda, omega is equal to twice pi nu. Then we have E is equal to h nu, and this can be written as twice pi h cross by h cross into nu. H cross is same as h by 2 pi. Reduced Planck's constant we call h cross. Then lambda is equal to h by p. Again we can write down for h 2 pi h cross by p. So psi now becomes, we put from the above in the first expression, psi is equal to a exponential minus I by h cross et minus px. Now mind it, E is the energy of the free particle and p is the momentum of the free particle. So a wave associated with a moving particle can be represented like psi is equal to a exponential minus I by h cross et minus px. We will again revisit this. We will revisit this one slightly later. Now let us come to, we will be digressing somewhat from this wave function psi to understand a wave function, wave equation, and then again come back to have a correlation between the two. Now what is a wave equation? We are quite familiar with this one. The wave equation is an important second order linear partial differential equation of the description of a wave. They appear in classical physics like mechanical waves, like water waves or sound waves or electromagnetic waves, which we'll see one by one. Now wave equation come up in the fields like acoustics, electromagnetism, fluid dynamics, etc., etc. For example, the wave equation for a stretched string is given by del 2y del x square is equal to mu by t del 2y del t square. It's a familiar equation. Y is the displacement, mu is the mass per unit length, t is the tensor in the string. So this is the wave equation associated with a string, for example. Now mind it, the solution of this wave equation will be a plane progressive wave, and this solution in terms of y we generally find out for a wave in a string or a sound wave or whatever wave. The solution of this wave equation can be of many kinds that reflects the variety of possible wave types. For example, a progressive wave, its solution could be a spherical wave, its solution could be a cylindrical wave. And now, a train of waves, like for example, I said, the progressive wave could be written y is equal to f t plus minus square root mu upon t x. Now this t upon mu is equal to v. So t plus minus vx you can say. Now minus sign stands for moving in the positive direction, plus sign stands for moving in the negative direction. So the wave equation for a stretched string becomes del 2y del x square is equal to 1 by v square del 2y del t square. And its solution is y is equal to a sin omega t minus x by v. Now this is one such wave equation in classical mechanics that we encounter. Here Y represents the displacement in the string. Here, this is the solution of that wave. Again, we revisit this particular figure. And this is one such animated figure I am showing for a plane progressive wave moving in a string. And you can see from here, now you can spot your eyes at a red point, for example. You can see that particles are not moving. They are doing simple harmonic motion about their mean position in the transverse direction. And the wave is moving toward right. Now, this is courtesy ISVR, University of Southampton. Now, this is again an acoustic longitudinal wave moving in this particular tube. You can see from here that we have compressions and rarefactions. And if you again spot at a red point, then you will see that this point is making to and fro SHM remain, it's about its mean position. It is not moving forward. All these red particles you can see, whereas the wave is moving forward. And this is how we represent an acoustic longitudinal. Mind it, the expression, mathematical expression for an acoustic longitudinal wave and the expression for a transverse wave will be the same, and they will be the solutions of the wave equation we have understood just now. And this is in red to mark the difference between the compressions and the rarefactions in the longitudinal wave. Now, courtesy University of Southampton again. Now, this is the wave. This is a string fixed between two ends, and this has been plucked, and we have, these are the modes of vibrations in the string that you already know. In the first one, we will have one loop. In the mode 2, we will have two loops. And you know, the frequencies are given by n is equal to p upon 2l square root t upon mu. T is the tension, mu is the mass per unit length, and L is the length of this one. So these are different modes of vibration of the string that we can see. And courtesy is again ISVR, University of Southampton. Now let us similarly go to an electromagnetic wave equation. Now this is same way written as del 2E del x square is equal to 1 by c square del 2E del t square. This is for, here we have electromagnetic waves whose wave equation is given by this, and in the similar way the solution is a plane wave. E is equal to E naught sine omega t minus kx, that is, it is an electromagnetic wave, plane progressive electromagnetic wave, or polarized, plane polarized also, moving in the positive x direction. And this is a wave you can see in a typical way, E versus V. Then, and here is an electromagnetic wave moving along the y-axis and oscillating along x. And you know, electric and magnetic fields are oscillating in an electromagnetic field, wave. So you see, just like we had the wave equation in the for mechanics, for sound waves, etc. Similar way, we have the wave equation for electromagnetic waves, and similar solutions mathematical exist for them all. And then we have the courtesy attribution to these sites and these persons, with a thanks to them. Now, here is the catch that we have to pick up. Now, what is the position of y, that is the displacement of the displacement in the case of sound wave or the wave in a string, or the electric field or magnetic field in an electromagnetic wave? What the position of those over there and the psi over here in the wave associated with the moving particle or the Broglie wave are similar. That means what is the position of y or E over there is similar as the position of psi over here. But one distinction is there, that psi is complex. Here y, E, etc. are physically measurable quantities. Psi is not physically measurable quantity. Now, this wave function psi, this represents the probability of locating a particle in a space at point x, y, z at the instant of time t. So mind it, this wave function psi is a definitive function. It has a definite value at x, y, z, t. But psi is a complex function. It can be positive or negative. And mod psi square, as we had seen earlier, mod psi square represents the probability density, that is the probability of locating the particle at x, y, z, and t, and that is given by mod psi square. So psi is complex. It can be positive, negative, but mod psi square will always be positive. So psi cannot represent the probability, rather mod psi square represents the probability density. Here it is. Now, a wave function similar to the wave functions we have seen in the sound wave, that is the in the string or in the electromagnetic wave, a wave function similarly in quantum physics is a mathematical description of the quantum state of an isolated quantum system, much in the same way. According to the superposition principle of quantum mechanics, wave functions can be added together or multiplied by complex numbers to form new wave functions and form a Hilbert space. Similar functions can be done with them. A wave function behaves qualitatively like other waves such as water waves or waves on a string because the this Schrödinger equation is mathematically a type of wave equation. And this is what we have to understand. Just like we have the wave equations in classical mechanics, in sound wave, in string, in electromagnetic waves, the Schrödinger equation is also mathematically a wave equation. And because it is a wave equation, its solutions will be the wave function psi, just like the solution of those wave equations where y, e, or h. Similarly, the solution of Schrödinger equation will be psi over here. Since the wave function is complex, only its relative phase or relative magnitude can be measured. Its value does not in isolation tell anything about the magnitude or direction of measurable observables. One has to apply quantum operators whose eigenvalues correspond to set of possible results of measurements to the wave function psi and calculate their statistical distribution for measurable quantities. So psi itself is not measurable, but it will give the probability function mod psi square will give you the measurable quantity. The results will be the measurable the measurement of the quantity, physical quantities, but psi itself is not a physical quantity. It's complex wave function. You cannot relate it to something physical. Now, the mathematical expression of the wave equivalent of a free particle of total energy and momentum p, just we had seen a couple of slides back, moving along x-axis, is given by this. Psi is equal to a exponential minus I by h cross et minus px. Now, for a particle subjected to some forces, a second order differential equation is proposed and formulated, and then that is applied to the special cases. Differentiate the free particle expression twice with respect to x and once with respect to t, then you will get this one. Del 2 psi del x square is equal to minus p square by h square psi, and you have del psi del t is equal to minus I e upon h cross psi. Then applied to non-relativistic case having the total energy of the particle is written as, now E is equal to P square by twice M plus V. For non-relativistic case, this total energy is equal to kinetic energy plus potential energy. Now multiply by psi on both sides of the total energy expression, then E psi is equal to P square by twice M psi plus V psi. E psi is, now let us use the energy operator, that is E is equal to minus h cross by I del del t, just multiplying by psi we have this expression, and the momentum operator, then we have p square psi is equal to minus h cross square del 2 psi del x square. Now let us put these two in the above expression and you get this. H cross by I del psi del t is equal to h cross square by twice m del 2 psi del x square minus phi psi. Now this is what we call the time dependent Schrödinger equation. The expression that we are seeing over here after this is the time dependent Schrödinger equation. In 3 dimensions, the Schrödinger equation may be written as this one. You can see that what we had as del 2 psi del x square, in the 3 dimensions, this will become del 2 psi del x square plus del 2 psi del y square plus del 2 psi del z square. Other things will remain the same. Here, particle's potential V is some function of x, y, z and t. Mind it, we have started from a free particle and we have calculated the expression for a particle having a potential energy also. We will just now discuss it. So h cross by I del psi del t is equal to h cross square by twice m, and the symbol Laplacian operator del square if we use given by this, then this can be written as h cross square by twice m del 2 psi minus v psi. This holds in all coordinate systems, whether it is Cartesian, whether it is spherical polar, or it is cylindrical coordinate. Now, just now what I said, there is a problem with this derivation of Schrödinger equation. We obtained the equation starting from a special case of a wave function of a freely moving particle, and then established a general equation having the potential energy also, which is a function of x, y, z and t. Is it plausible? Is it okay? Then we have no way to prove that this method of establishing the equation is wrong or correct. We cannot say that. What we can say, what we have in our hand is to straight away postulate Schrödinger's equation. We postulate Schrödinger equation, solve it for different variants of physical conditions, and compare the results of calculations with results of experiment. We don't go for whether we can derive this way or derive that way, or we cannot do that. We postulate Schrödinger equation, solve it for different conditions, match it with the experimental results. If they match, accept it. If they don't match, discard it. Schrödinger equation cannot be derived from the first principle basically. Why? Because Schrödinger equation is the first principle in itself. It is in itself a first principle. So you cannot derive it from some other first principle. The equation is a postulate in the same sense as the postulate of a special relativity or laws of thermodynamics. They have been established based on varied experiences. They are not derivable. They are themselves postulates. In the much similar way, as they are the fundamental generalization, valid as empirical data, Schrödinger equation can also be postulated. And just like that, I have said that their results should be compared with the experimental results. If they give the closer results, accept them. If they don't give, don't accept them. But fortunately, Schrödinger equations have given very, very accurate results in almost all the areas. Form of Schrödinger equation depends on the physical situation. The most general form is the time-dependent Schrödinger equation, which gives a description of a system evolving with time. And this is time-dependent Schrödinger equation that I have said. This is a general one. In a nutshell, because the quantity in the parenthesis is nothing but the Hamiltonian, so this time-dependent Schrödinger equation can be written as IH cross del t psi H psi Hamiltonian psi. The general equation is indeed quite general, used throughout quantum mechanics for everything from the Dirac equation to quantum field theory by plugging in various complicated expressions for the Hamiltonian. The specific non-relativistic version is a simplified approximation to reality, which is quite accurate in many situations but very inaccurate in others. Time-independent Schrödinger equation that we use for a steady-state solution of the wave function psi. And that describes the stationary states. That is, here we have. The V is removed from here, you can see. Psi is a function only of x, y, z. And the eigenvalue equation comes out to be E psi is equal to H psi, where again H is the Hamiltonian. When the Hamiltonian operator H acts on a certain wave function psi, the result is proportional to the same wave function psi, then psi is a stationary state and the proportionality constant E is the energy of the state. Mind it, generally whenever we solve this equation for any system, then we have values of E coming out to be discrete. E does not come out to be continuous. Now this does not mean that there is difficulty in solving this equation or this equation in getting continuous values of E. Rather, the quantization or the discrete value comes as a natural consequence in quantum mechanics. For example, if you solve it for the hydrogen atom, E will have discrete values of energy minus 13.6 electron volt, minus 3.4 electron volt, minus 1.51 electron volt, minus 0.85 electron volt, etc., etc. for n is equal to 1, 2, 3, 4, etc. In large number of cases, the potential energy V is not a function of time, but a position only. For such cases, any reference to time is excluded. So in this one, if you club, you distinguish between the time function and the xyz function, then you can remove time dependence, and then you will be getting finally as del 2 psi del x squares plus 2m by h cross square e minus v psi is equal to 0. Here v is a function of x, y, z only, not of time. So this is time independent Schrödinger equation. In quantum mechanics, the analogous of Newton's law is Schrödinger equation. What happens in Newtonian mechanics? You apply a definite amount of force, you get a definite amount of acceleration, a definite amount of displacement, a definite mass of the particle is there. So everything we talk about in Newtonian mechanics are definite. We apply 1 Newton force, an acceleration of 1 meter per square second will be produced in a mass of 1 kilogram. There will be displacement this much in this much time. All the things are definitive. But if we solve the Schrödinger equation and get psi, and then we make mod psi square, then you will see that we do not get definitive values in the subatomic world. That is, the solution of Schrödinger equation does not predict definitive value. Here we talk in terms of the probabilistic values. For example, if we have to express the first Bohr radius, how do we say it? We cannot say that the first Bohr radius is 0.51 angstrom. No. What we can say that if we make large number of measurements of the first Bohr radius, large number of measurements, then the most probable value of the radius will be 0.51 angstrom. Everything we measure in quantum mechanics are all probabilistic. The wave function is the most complete description that can be given of a physical system. Solution to Schrödinger equation describe not only molecular, atomic or subatomic systems, but also macroscopic systems, possibly even the whole universe. Now let us apply Schrödinger equation to solve a problem in per particle in a box. This is the particle in a box. Left hand side, Vx is equal to infinity. We have a tall wall of energy. On the right hand side also, Vx is equal to 0. On the both sides, we have the barrier, but in between, Vx is equal to 0. So inside, we have only the kinetic energy associated with the particle. Now this is the mathematically that we can express that Vx is equal to 0 for x lying between 0 and L and is equal to infinity otherwise. And if we solve then the second order differential equation, Schrödinger differential equation, these are the wave functions that we get for different n. And if we try to plot these wave functions, we are getting this one. For n is equal to 1, 2, 3, these are the wave functions. And if we try to plot the energy versus k graph, we are going to get this. And these values that the dots are reflecting, dots are pointing out, these are the discrete energy values that we'll be getting as a solution for the particle in the box. The particle will have only these values of energy which are given by the dots. And here is the expression for E versus K, and here is the expression for E versus N. On solution of this one, on normalization, we can get this one. So this is the solution of the particle in a box. And if we try to see the wave function associated with the wave function associated with the of the wave rather for the particle in the box, then we will have this one. You can say what is A? This is the classical particle in a box. It has only kinetic energy. It is bouncing back and forth between the two sides. This is a classical picture. And if we go to the quantum mechanics, you can see B, C, D, etc. And what do we see? That if we associate a wave with the particle, then the wave functions associated with this particle are going to be plotted like this, and these wave functions will be behaving like this. You can see from here. And of course, the courtesy. And let us make a comparison to already that we have discussed, that is the modes in a stretched vibration of a stretched string fixed between two ends. You can see this particular one, first one that we can see is same as this one. The second one is same as this one. Third one is same as this one, and so on. You can see from these places that we have the same analogy that we had in the classical mechanics and that in the quantum mechanics. So we have a continuity from the classical mechanics to the quantum mechanics, whether it is the wave equation, or it is the solution of the wave equation, or it is Y-E resembling psi, or the wave function, nature of the wave functions that we have, only with the difference that psi is a complex it cannot be related directly to the physical quantity. And here, mod psi square gives the measurement of in terms of probabilities, whereas in classical physics, we have definitive values. And courtesy, again for this one that I have already given, to ISVR, University of Southampton. Now, if we have the two-dimensional box, these will be the wave function. If we solve them for two dimension, then these will be the wave functions associated. These are the energy values, and this will be the plot of psi, x versus x and y. And let us see what we have seen by far about wave function psi. Number one, Newtonian mechanics versus quantum. That I have seen. Newtonian mechanics is about definitive values. Quantum mechanics is about probabilistic values. That is, in the macroscopic world, we have definitive values. In the subatomic world, where we apply quantum mechanics, we have probabilities. We talk in terms of probabilities. And similar to what we have, the wave equations in Newtonian mechanics, similar wave equation is there in terms of the Schrödinger wave equation in quantum mechanics. Solution over there are y, e, h. Here the solution is psi. Those quantities y, e, and h are real quantities. Psi is a complex wave function. Psi cannot be related directly to some physical quantity. Y, E, and H can be related to physical quantities. Naturally, the mod psi square will give you some measurement of probability. So we have psi is a complex, mod psi square represents the probability density, just the way we have Y and E for displacement of and electromagnetic wave. Psi is the wave function of the wave associated with the moving body. The speed of the Broglie wave is same as the speed of the body. We have already seen it. Psi is formed by superposition of infinite number of sinusoidal waves differing from each other by delta omega delta k. A wave called the matter wave or the Broglie wave is associated with the moving particle, leading to uncertainty in the position of the particle. The moment we associate a wave with a particle, you have an uncertainty inherent in the system that you will find when you try to locate the particle. Now, psi is certainly a solution of the Schrödinger equation. And Schrödinger equation in itself is a postulate like the theory of special relativity or the laws of thermodynamics. And here is a very simple joke taken from, let us say, the internet. A fellow is saying, basically, I came here as an undergraduate to look for girls, as it happens in the youth, accidentally got hooked on quantum physics and have been here ever since. Mind it, quantum mechanics is a very, very interesting field. And if you understand this, only that it is interesting to, otherwise certainly it is boring. And while making a transportation or making yourself coming from classical physics to quantum mechanics, it is not just a jerk from classical to quantum. Rather, it is a continuity from classical mechanics to quantum mechanics. And that is what I have tried to establish today in my lecture on the Broglie waves leading to Schrödinger wave equation. Thank you very much for your kind attention. Many of my lectures are uploaded on the YouTube on selected topics in quantum mechanics. You can visit them over there. If you can like them, and if you subscribe to them, then the notification will automatically come to you when the next lecture is uploaded. So do visit YouTube link of mine, and you will get so many lectures on